Boleh dengar saya? All right, good. Okay, so we're still in thermal oxidation, the last part. Today we're gonna look at dopant redistribution during oxidation process. So by redistribution, what I mean is we're gonna look at how the dopant changes their profile and properties during the oxidation process. So we have learned that when we run the oxidation process, it's going to involve consumption of the silicon wafers from the surface. So as the process progresses, more and more silicon is going to be consumed. So the oxide is going to penetrate into silicon as the process goes on. So if you have dopant profile or dopant with some concentration before the process, and then you subject the wafers to oxidation process, so the wafers or the surface is going to experience dopant redistribution during the process. Okay, so each of the common dopants that we use for our doping process, we're going to learn later on details, um, is going to show slightly different behavior. Okay, so all right. So if you look at this slide, you can see the slide, the dopant redistribution slide. Okay, good. Um, Dopant redistribution can be calculated by the equation below. M equals to equilibrium concentration of impurities in silicon versus equilibrium concentration of impurities in silicon dioxide. So impurities here refer to the dopants that we use in our silicon. So if you're talking about phosphorus, so we're talking about the M value of phosphorus. So if you're talking about boron, then we're talking about the M value of boron, okay, at the interface of silicon and silicon dioxide. So during the process, due to the redistribution during the oxidation process, if you use different dopant, so they're gonna have, when you say it is a ratio, so that means the value can either be more than one or less than one, because concentration of the dopants in silicon and in silicon dioxide is going to be different. So if you have M more than one, so that means the concentration of the dopants in silicon is higher than the concentration of silicon dioxide at the interface. Okay, you can see in the first illustration there on the left hand side, where at the interface, yang vertical line tu the dopant profile. So the y-axis here is the doping concentration, if you like. So here the silicon is higher than silicon dioxide. So therefore the M value will be more than one. Okay. On the other hand, have dopants with M less than. So, and if you have the dopants inside your silicon, so it's going to show this kind of redistribution during the oxidation process. So you can see here on the right hand side, the concentration of the dopants in silicon is less than the doping concentration, the equilibrium concentration of the dopants in silicon dioxide. So therefore M is less than one, because silicon has less dopant concentration in comparison to silicon dioxide. Or you can also put this as C1 over C2, okay, with C1 referring to silicon and C2 referring to the oxide. So let's have a look at detail of what's happening. So dopants affect device performance. So the moment you have redistribution process, so this is not what you intended in the first place, but this is the intrinsic behavior of the dopants during the process, so particularly at high temperatures. So the change in dopant location and concentration during oxidation can affect device operation, of course. So you need to know what is the dopant concentration and profile before the process as you intended, as you got after your diffusion process. We're going to learn later on. And you need to know as well the doping concentration and the profile after the oxidation process, because redistribution has just happened, right? So dopant redistribution depends on two things. The first one is the diffusivity of the impurities or the dopants in this case in the silicon or silicon dioxide. So the first one is diffusivity, and the second one is the segregation coefficient, right? Segregation coefficient of the dopant in the material. So these are the two factors that affect this redistribution mechanism during the oxidation. N-type dopants move deeper into silicon, so high concentration at the silicon dioxide interface. N-type dopants such as phosphorus arsenic tend to pile up at the silicon interface, so giving higher concentration of the dopants at the silicon, so giving M more than 1, because M silicon is the concentration in silicon is higher than concentration of oxide, so you're going to have M of more than 1. On the other hand, P-type dopants move into silicon dioxide and deplete silicon layer. So P-type dopants, for example, boron, tend to be depleted from the silicon into oxide, so leading to higher concentration of the dopants in the oxide in comparison to silicon. So since silicon is lower than the oxide, so you're going to have M of less than 1 for borons. So let's look at a few examples. Case 1, oxidation, boron doped silicon. So you have your boron doped silicon to begin with, and then you run your oxidation process. So M for boron is about 0.3. So this is what you're going to see at the interface. So this vertical line here is the interface. On the left hand side is silicon dioxide. On the right hand side is silicon. So after the process, you're going to see that boron given by C1 in silicon, C2 in oxide, is depleted. So your boron is depleted from silicon going to the oxide, giving your M to be more than less than 1. Okay, so C1 is less than C2, and the ratio is about 0.3 for boron. So on the other hand, if you talk about N-type dopants such as phosphorus, arsenic, antimony, so the M of these dopants are more than 1. So more than 1. So what's actually happening at the interface here, the vertical line? So the same, just like the previous one. So oxide is on the left, silicon is on the right. C1 shows concentration of your N-type dopants in silicon, and C2 shows your N-type dopants in the oxide. So due to the properties of the N-type dopants, your C1 will be higher than C2, leading to M of more than 1, right? C1 is higher than C2 due to the piling up of the dopant near the interface. These can also be summarized as these four charts, if you like. So the first case, A, is for boron. So boron, just now we've seen that boron tends to be depleted, right? Tend to be depleted from the silicon. So leading to here C1, if you like, less than C2 or C over CB pun boleh juga. This is just another representation. tapi dia punya ratio remains the same. So it's about the concentration of impurities in silicon over the oxide. So giving M of about 0.3. So on the other hand, if you use boron but with hydrogen ambient as shows here in B, so the diffusivity is going to be faster. So you're going to end up with more borons being depleted, so lower value of M, so more depletion from the silicon, depletion of boron from the silicon. For the C, you can see here, due to the piling tendency of piling up of the phosphorus, you're going to have more phosphorus at the surface of the silicon. So C1 over C2 or C over CB is going to be more than 1. So the value is close to 10. So you also have gallium. So gallium is on the lower right. So gallium is a fast diffusion in silicon dioxide. So let's look at the value now. What's the values of the redistribution? Let me share one web page to you. On redistribution. Okay. Okay, can you see the web page? About can you see this? Okay, good. So tengok sikit ya, dia punya description here. So let me just move this stuff around. The redistribution process depends on the ratio of solubility of the doping material in silicon and silicon dioxide, or given by M equals to C1 over C2. So at the silicon dioxide interface, the dopants are redistributed by segregation until the ratio of the concentration at the interface is same as the ratio of their solubility, right? So the concentration is also affected by the segregation of the dopants in both materials, silicon and silicon dioxide. So the ratio of dopant solubility is expressed by the segregation coefficient here. So this is also proportional to the concentration of the dopant in silicon and silicon dioxide. But in this case, it is also M, but then it refers to the solubility of impurities in silicon over in silicon dioxide. But this ratio is actually proportional to the M value, which reflects the concentration of the impurities in both materials. So if you look at this, look at the second paragraph. There are dopant species which solubilize better in silicon dioxide than in silicon. So for this case, where dopants solubilize better in silicon dioxide than in silicon, so you're going to have M of more than less than 1, because you're going to find more impurities in the silicon dioxide in comparison to the silicon. Okay, so it is solubilized lebih senang dalam silicon dioxide, so you're going to find more of concentration in the oxide, so you punya C1 over C2 will be less than 1. Okay, and the species which have reverse behavior, M is more than 1, has better solubility in silicon in comparison to silicon dioxide. So you're going to find more of them in silicon in comparison to silicon dioxide. So therefore your C1 is higher than C2, and your M1 therefore is higher than M is more than 1. Okay. So this is another way of description. In the case of M of less than 1 for boron, we've seen just now, boron tends to be depleted from the silicon going into silicon dioxide. The dopant concentration, boron, is enhanced at the silicon dioxide interface, whereas beneath the interface, there is dopant depletion in the silicon. So dopant is depleted in the silicon. You can find more of them in the silicon dioxide. For reverse solubility ratio, which is more than 1, also reflects C1 over C2 more than 1, like phosphorus. Only few dopants penetrate at the interface, so they tend to pile up, and you can find more of them into the silicon. So you're going to have a higher C1 compared to C2, therefore M is more than 1. Therefore, the concentration phosphorus in this case, the silicon surface is enhanced, so giving M higher than 1. So let's look at the values here. So dopant species or M. So the for boron is typically between 0.1 to 0.3. So that means you can find more of boron in the oxide in comparison to the silicon due to the depletion of the boron during the process. On the other hand, if you look at the N-type, like phosphorus, arsenic, antimony, they are 10, and gallium is even higher than that, even though it's p-type as well. So boron and gallium are p-type, but the M behavior, if you like, is completely opposite. Gallium tends to pile up at the silicon interface, so you're going to have more than M of more than 1. So in this case, it's 20. On the other hand, boron tends to be depleted out of silicon, so you're going to have M of less than 1. So it's about 0.1 to 0.3. So N-type dopants like phosphorus, arsenic, antimony exhibit the same behavior. So M is about 10. So figure 4.1 down here is similar to what I've shown you just now in the slides. So yang left-hand side is, what is left-hand side? Apa example of left-hand side punya dopant? So what do you see here? M is less than 1. So therefore, the examples of the dopants are, apa example ya for the left-hand side? And when M is less than 1, so what is the, yeah, it's boron, right? It's boron because boron is depleted during the process or redistributed during the process. So M less than 1 refers to boron, and on the right hand side it's for the phosphorus, arsenic, antimony. Okay. This one is another description. Tapi sama ya, what it means is exactly the same. So I'm just gonna go back to the slides now. Okay. You can see the slides now, right? Can you? Yep, good. Boron with hydrogen ambient boleh explain balik tak? Boleh, bro. Boron dia okay. Apa beza boron without hydrogen and boron with hydrogen? Let me read to you the full explanation. Dia akan jadi fast diffusion in a hydrogen environment. Okay. Okay. The presence of hydrogen, so boron adalah hydrogen. If you look at the okay, on this slide, if you compare the top left and top right, A and B, so A is without hydrogen, B is with hydrogen. So kenapa dia punya M is much lesser with hydrogen? Kenapa? So the presence of hydrogen during oxide growth or impurity diffusion greatly enhances the diffusion of boron through oxide. So itu the reason. So remember just now I told you when we just started that the redistribution depends on two things. The first one is the segregation coefficient, and the second one is the diffusivity of your dopant in silicon and silicon dioxide. So in this case, when you have hydrogen environment, dia akan boost dia punya diffusivity of boron in oxide. So you end up having more boron dalam oxide sebab dia akan tend to be more depleted. Okay, so you're gonna end up with more and more depletion of boron from the silicon. Dia macam sucking lah. Okay, you macam suck more and more boron from the silicon into oxide. So you're gonna end up having more of boron in the oxide in comparison to silicon. Oxide yang you ada boron tu is boron in the oxide now is more compared to boron in the oxide tanpa hydrogen. Okay, so kalau tak ada hydrogen, dia punya diffusivity is not so great. So, but with hydrogen, dia akan enhance diffusivity of boron dalam oxide. Okay, so that's gonna lead you to more depletion of boron from silicon and more going into silicon dioxide. So C1 over C2 is gonna be much lesser now in comparison to without hydrogen punya condition. Okay, Shah? So the difference is only in the diffusivity of boron with hydrogen. So dia akan boost the diffusivity of the dopant of the boron. So maksudnya kat sini, when you run the process, katalah you already know what's the M is typically like when you run certain processes. So kalau you tweak by inserting hydrogen, for example, you dah run oxidation process macam biasa, you're gonna you have oxidation running, then you have boron already in the system, silicon dioxide system, and then suddenly you process you tambah hydrogen on top, di mana you masukkan hydrogen gas dalam proses tu, so punya boron diffusivity will automatically enhance that system yang you ada. Okay, so you can actually manipulate this to the advantage of the devices, or you might also want to prevent this if it will lead to detrimental effects to your devices. So this is only the basic. Cumanya how you gonna use it, or whether or not you're gonna use it, or you want to prevent it do. Cumanya this is it during the process. If you talk about the real wave process, so this is going to happen in diffusion oxidation process. Typically, it's under one department. If you talk about Siltera, I'm not sure about other fabs. So in Siltera, diffusion and oxidation process, both processes are controlled under one department. Okay, so maksudnya if you are the process engineer for oxidation, you're gonna look into all this stuff, right? So kalau you punya device or oxide ada problem, ada poor quality or something, or dopant distribution is not as intended, so this is the thing that you have to know, right? Okay, Shah? Shaira, is it right? Keliru dengan graf dia. Okay. So let's look at the value of the, let me see what the value of the M. Ya, saya tengok dia punya value of M. I think with the value of M, maybe you can see clearer. So let me try to see if I can find M value for hydrogen. Give me a few seconds. Let's think of that. Is there a value of M at all? Fast diffusion. Kalau ni dia tak bagi value of M, okay, let me find for you later on the value of M, the value of M for boron with hydrogen. Okay. Yes, the value of C1 should be lesser. Exactly. Cumanya nanti kita tengok the value of M for boron with hydrogen in comparison to boron without hydrogen, or is it just within the range of 0.1 to 0.3? Can you remind me of the M value? Okay, nanti saya try search. Dalam buku ni tak ada M value. Dia cuma bagi satu range of M value for boron is typically 0.1 to 0.3, but it did not state explicitly the values of M under hydrogen and without hydrogen. Do you remind saya? Okay, let's go on. So you can see the slides now. Nampak kan? Okay, good. So let's move on to this. We are almost done though. Okay, polycrystalline silicon oxidation. So we have learned that polycrystalline silicon is a silicon with multiple grains. So the size of the grains can be as small as microns, or it can be as big as if you like. But typically, if you talk about a very thin layer, then it should be micron or even nanometers. Okay. Kalau you talk about silicon yang besar, then the grain can actually be size, millimeter size, or in fact centimeter size. When I work on my PhD last time, saya work on polycrystalline silicon on glass. So the thickness of the crystalline silicon is about 10 microns. So that's about our hair divided by 10. So cross section is about 10 lah. Cuma bila saya pakai glass tu, saya pakai glass yang besar. So that's about 5 by 5. Saya punya glass tu is about 5 by 5 cm. So that's like 1/3 of pembaris pendek kan. 15 cm. So 5 by 5, so the whole surface of this glass is actually polycrystalline silicon. So bila saya pergi ke etching process, I remove some of the surfaces, so I can actually see the grain size. So maksudnya in that particular case, so the grain size can be as big as centimeter by centimeter squared. So when we talk about grain sizes, so it is not necessarily very small, like nanometer squared or micron squared. It can also be squared. It can also be micron squared. It can in fact be cm squared as well. So it depends on where do you look at the grain. Okay. So if you talk about a very thin layer, just like I said now, if you look at a very thin layer, then of course you're talking about so most likely in our IC fabrication is nanometer squared. It must be very, very small. So even though they are small, but being there as polycrystalline silicon with grains, multiple grains, and grain boundaries between the grains, it will also affect your oxidation process in terms of the growth rate. So biasanya kalau dalam IC fabrication kita akan pakai monocrystalline silicon. So you won't see this problem on this slide because we are using monocrystalline silicon to begin with. So there's no grains, no multiple grains. There's only one grain infinite. So there's no grain boundaries at all. So if you talk about solar cell, for example, which also use polycrystalline in some cases, so about some technologies use monocrystalline to fabricate solar cells. Some other technologies use polycrystalline to fabricate solar cells. So in that particular case, you need to know this. Okay, the moment you do the oxidation, you will see different growth rate, grade, and in comparison to the grain boundaries. So as a result, due to the different growth rate, which means the oxide, the grain boundary is going to grow a lot faster than within the grain, which is a bit slower in terms of the oxidation. So kita akan dapat eventually after the process, you're going to see some roughness on your silicon features due to the different growth rate lah. Sebab bila you ada polycrystalline grains, depends on how do you grow the polycrystal grain in the first place. So typically polycrystal grain tu dia akan random in nature, random in sizes, random in orientation. Macam you tengok dekat gambar belah kanan ni, fast and slow tu, you can see that the grains are randomly oriented. So that means that you nampak satu kotak tu is just a single crystal, then you have a grain boundary, and the neighboring grains are tilted at different angles and so on and so forth. So they are random in nature. So you cannot plan or you cannot know exactly what's the growth rate difference in comparison to when you compare oxide and your silicon. So maksudnya that leads to formation of roughness on your oxide as shown by the bottom left here. So you can apply, this is your original silicon if you like, just for illustration. This is the interface of silicon and the oxide, and the silicon is consumed of course, and then you're going to end up with oxide that is quite rough on the surface. Okay, so so this is owing to the different growth rate within the polycrystalline silicon. So you won't see this on monocrystalline silicon because the growth rate will be exactly the same throughout the area. Okay. All right, so after we finish with our oxide, so we've done with the thermal oxidation process. I'm going to give you some questions about oxidation during your assignment 1, maybe this week or next week. Most likely next week, I think. Okay, you're going to do some calculation as well on the oxide in your assignment 1. So after the oxide growth, there are few characterizations that you have to do in order to make sure that you have a good oxide after the process. So the first one is, of course, surface inspection. It can be as simple as microscope. It can be an SEM characterization. It can be some other form of characterization, or we call it visual inspection, in order to see what you get on the surface. Even though our interest is only in the oxide thickness, uniformity, integrity, so on and so forth, in the fab, you also have to look for particles, right? Particles is what you typically see from your first inspection here, surface inspection. So if you talk to any diffusion or oxide engineers, particle problem is one of the biggest challenges in the fab. Okay, particle problem datang dari mana? It can be from your quartz board, it can be from your gas line, it can be from your wafers, it can be from your whatever the ambient that's running the process. It can even be the incoming particle from previous process before you actually run the oxidation. So that's why you need to do the optical surface inspection to make sure that your surface is clean and the particle count is less than the spec. So dalam fab we normally have a process spec. Specification to is what we call process. Let me write down. So setiap proses dalam fab dia ada proses spec, proses specification. Nanti if you go to internship dalam wafer fab, you will probably see this. Setiap proses dia ada dia punya process specification. So dalam proses spec tu dia akan spell out clearly what sort of thickness do you want to have for your technology A, technology B, technology C using dry or wet ox. What is the flow rate of your dry oxygen? What is the bubbler punya temperature and so on and so forth in order to do the oxidation process, temperature, time, ambience, blah blah blah. The RAM rate of the furnace before the process, the cool rate of the furnace before the process, and also the particle count after the process. So particle count dia akan outline lah. The process can only tolerate a certain number of particle counts of certain sizes after the process, of which kalau you fail, so katalah dia can only accept up to 5 particles after the process, but your process has about 10 or 15 particles after the process, so the wafers yang you dah process dalam oxidation cannot proceed. They just have to be stopped. They're gonna be on hold. We call it on hold in the fab. Dalam fab processing we call it on hold. So the wafers or the lot yang handle the wafers tu satu lot ada 25 wafers. So that particular lot is gonna be on hold due to the particle count failing the spec, right? Failing the process spec. So maksudnya selagi mana you tak troubleshoot the problem, whether it's due to the process or the recipe or the equipment or the gas or incoming problem, the wafers cannot proceed the process, cannot proceed to the next processes. Okay, maksudnya duduklah kat situ sampai process engineers or equipment engineers come in and troubleshoot and find the root cause and solve the root cause and make sure that it doesn't happen again in the future. then only you can release the lot. On hold dia punya opposite dia is release. Release the lot dalam processing punya platform. Ada software we call it factory work dalam if you talk about Silterra, then Silterra is using factory works to govern the whole processing of the fabrication from day one until the final day before it's shipped out to the customers. Okay, so that's how it looks like. Then other than the surface inspection for particles, your process spec also outlines what's your oxide thickness, the targeted oxide thickness. So you're going to work with SPC or statistical process control chart or SPC charts. So there'll be say your targeted thickness is about 5 nano, so your process spec will actually outline how much is the plus minus of the process that it can be tolerated. For example, if you talk about 5 nano, then maybe, I don't know, you can tolerate 0.3 nano plus minus. So that means if your oxide thickness is 4.7 to 5.3, the process is fine. If your process, if the oxide thickness measured is 5.4, so it's gonna fail the spec. Then the wafer is gonna be on hold, waiting for you as process engineers to come and troubleshoot, find the root cause. Then only you can release the wafers for the next processing. Okay, so it's called process spec. There'll be on the process spec dalam SPC chart tu, there'll be target 5.0 nanometer. There'll be upper control limit 5.3, lower control limit 4.7, assuming that the plus minus is 0.3. If you move to technology node yang lebih latest, yang lebih smaller, so your plus minus is going to be smaller as well. If previously you control plus minus 1, then probably now you have to control plus minus 0.3, for example. If you go further down, then probably you have to control plus minus 0.1, 0.2. So that means that's why your fluctuation too has to be very, very minimal. So that's the job of process engineers and equipment engineers in the fab. Okay. So have a read on SPC chart. Have a read, statistical process control. It's gonna be very useful if you go for your LI interview nanti, right? Few more things saya akan ajar nanti along the way, but I'll just mention it anyway. Failure mode and effect analysis, things that you have to pay attention to, give some time to read. Failure mode and effect analysis. Ini semua troubleshooting tool lah, SPC, 8D report. Baca je, tak faham nanti kita boleh discuss on this, no problem. What else? SPC, Six Sigma, the mic ni dia punya step to do your process improvement. So Six Sigma, the mic ni DMAIC itu is what you need to do in order to do process improvement on your process or on your product, on yield or whatever. Define, measure, analyze. Ini semua penting improve, control. So you have to do this in sequence. You first define what is the problem. So you measure how much is the problem, how big is the problem. Then you analyze the problem, analyze the data. Then you improve your process. Then you control the process so the problem won't happen again. So it's called Six Sigma method. So adalah ni dia punya level, green belt, black belt, yellow belt. Paling top sekali belt lah. Macam taekwondo lah. So they had a belt certification for that. So even better, if you have time, go for professional certifications online to get some belt on Six Sigma. It'll put you on edge over other candidates during the interview. Okay, banyak lagi lah nanti saya akan sebut along the way. Tapi the typical basic, if you talk about wafer fab punya engineers punya requirement, is 8D, SPC, FMEA, Six Sigma. Those are the typical keywords that are required as a process engineer, especially if you're talking about experienced process engineers. Kalau baru ni mungkin dia tak minta lagi lah, tapi at least dia mungkin tanya you, have you learned anything on Six Sigma or 8D report? So try to do some reading on this before your internship interview. Trust me, you're gonna have some bonus marks. Sebab dulu saya pernah interview new engineers you are. So the moment you know this, then you already have extra marks over other candidates. And eventually oxide cleanliness. So you want to make sure that oxide is clean. There are a few measurements for this. There are multiple characterizations that you can do to. In fact, there are more than these characterizations. Yang saya letak ni is only the simplest one lah. Simple, banyak lagi characterization. So the more crucial the device is, so if we're talking about 100 nano technology node versus 7 nano technology node, of course 7 nano punya technology node akan impose more controls, more characterizations, tighter process spec, and more maintenance and everything to the equipment to make sure that your results are always repeatable with a tight control. Okay, so these are only among characterizations, not everything. Kalau nak tahu everything, you kena tengok. One thing you can do is, if you want to know, you can go online. If you want to know what does it take to become a process engineer for oxide ataupun oxidation process lah, you can search online JD process engineer. Jadi itu job description, job description. Cuba tengok apa yang diperlukan. What is required of you to be a process engineer, either it's fresh or experience. You boleh tengok job description, JD ya. So bila orang sebut JD tu is actually job description. So read on the typical requirements. You can. That's why saya minta you, saya tak you LinkedIn account tu. Have you done it already? I've seen some of you have got your JD. Yeah, some of you have got your, sorry, not your JD, not have you got your LinkedIn account. So you can see on LinkedIn where HR or companies advertise vacancies for process engineers or fresh engineers or other equipment engineers or product or quality or customer engineers or reliability or whatever lah. So you one way to do it is you can browse the requirements, try to understand what does it take to become that engineer, so and see what you have so far, because eventually when you go for your interview you have to sort of match what you have with what the job requires. So that will, so maksudnya you buat benda tu dalam keadaan sedar lah, you do it consciously, you plan to get there. Bukan maksudnya based on what you dah ada, what do you grab, dan tengoklah apa yang ada, then you just try your luck lah. So kalau if you can recall Pro Asma punya typical dia punya famous motto, if you like, you have to do it by design, not by choice, right? By design. So you plan, you look at it, you plan, you look at your background, what does it take, what do you have, what you don't have, try to improve on what you don't have so that you matches better to the requirement. So yeah, that's it on oxidation. Shall please remind me on the M value if I can find for hydrogen. I would like to know as well the difference between hydrogen and without hydrogen for boron. Then other questions on oxidation. I'll give you your assignment 1 either this weekend or next week. It's going to be a written assignment yang menulis. It's going to be some description and calculation. It's going to be individual based assignment. So you're going to be given, I think, 1 week, if not mistaken. I'll have to look at the due date again and submit on eLearn as what you did last time on grade 6. Okay, ada soalan on oxidation? We'll move on to lithography next week. It's going to be more exciting. Ada soalan tak? All good so far? No for now, right? So can everyone follow before we go to the lithography? Senyap means okay, So senyap ni, saya pernah beritahu kan, senyap ni banyak mana. So I'll take that as okay, right? As understood, good. Right, yeah, reply macam tu lah pun, nampak semangat sikit. Okay means okay. Okay, you say okay. Not okay, you say not okay. I'm fine. It's not wrong to be not okay. Okay, the okay is okay. Just let me know, then I'll see what I can do about it. Okay, so I'll see you again next week. We'll look at how do we do patterning process by lithography. So lithography is printing by light, I told you before. So just like how you print your baju t-shirt kat sini, but instead of using screen printing process baju, kita akan print features or circuit using light in lithography process. So we're gonna also look at how do we do patterning of the oxide that you have just grown from the thermal oxidation process this week. Right? So I'll see you again next week in lithography. Bye-bye. Assalamualaikum. Take care. Have a great weekend.